Hi, I'm Nick Ackerman.
And I am Isaac Roshek, and today we are going to be going over the take-home Exam 1, and specifically Problem 2 for Civil Engineering 291.
We're going to start with Part A. For Part A, we're asked to find the amount of BOD remaining in a lake over a 6-day time period, assuming that BOD will decrease as seen in the function below.
We would complete this using 4 different methods. We were given initial values for BOD of 15 milligrams per liter, as well as a value of KD being 0.55 per day.
We'll start with Euler's method. It's an iterative process which defines DO as its current value plus the change seen in a specified time interval. More simply, Euler's guesses a new value by assuming a constant change between the current value and the next value. The constant change is equal to the slope or the rate of change of the function at that initial time. This method is good, however, it will break down when analyzing functions that change nonlinearly and when too large of a time interval is selected.
We began by opening up MATLAB and creating a folder labeled Exam 1. We then opened up a script file defining our time interval, the time range, which is 0 to 6 days, as well as our initial value of 15 milligrams per liter.
To define our BOD at a time interval, we needed to create vectors of both time and their corresponding BODs. To complete this, we used a for loop where I indexed our time and LE was our remaining BOD. As discussed earlier, we defined each element by adding the predicted change onto the previous BOD value.
We moved on then to our predictor-corrector method,
which is simply an extension of Euler's method, and as the name suggests, it offers a way to give a better estimated value. To do this, the same value is calculated using the Euler method previously described. However, the slope at that calculated point is averaged with the current slope. This new average slope is multiplied by the time interval to provide a better guess at how the value will change. Adding the change to the initial value gives the new value.
So once again, we started off with the same range and time interval as well as the same initial value. We then use the predictor method, which uses the same process to index our time and define each element of the BOD vector using for loop. However, instead of defining the next element directly, we first defined a predictor value, and then the slope at that predictor value is averaged with the current slope to produce a more accurate estimate of our change. And in doing so, we define each value element-wise for BOD. We then switch to the rung-kutta method.
And the rung-kutta method is an extension of the predictor-corrector method. While the predictor-corrector method only looked at 2 values, rung-kutta looks at 4. It looks at the slope at the initial point, the final point, and it looks at 2 points in the middle. So the same way the predictor-corrector improved on Euler's, rung-kutta improves on the predictor-corrector method.
When using the rung-kutta, we defined our function externally. To do this, we opened up a new script file and labeled it as f, and we defined our call value for the function as f. We then used the existing command in MATLAB of ODE45 to complete this process. We inputted our function f as well as a time range of 0 to 6 days and an initial concentration of 15 milligrams per liter. In doing so, we defined vectors for T and L for the rung-kutta method, which we could use to plot later. Finally, we switched to an analytical solution. So we first defined our variables that we'd be using in this method, and then we used the existing MATLAB command of dsolve to complete this process. We defined capital DL being the differential equation for L of our KD, negative KD value times L, and we also defined our initial concentration. We then had to hit the play button, and in doing so, the MATLAB solved our L equation for us and gave us a solution as seen here. In order to plot this function for L, we needed to create a for loop. In creating this for loop, we were able to define this L element-wise, and we were able to plot it. So that brings us to the last step for part A, which is plotting.
To plot these, we used the subplot command and created a 2x2 matrix, and then assigned each plot to a different point within that matrix. So the Euler method gets plot 1, and the predictor corrector 2, run cotta 3, and the analytical 4. We were also asked to find the BOD remaining at time 1.5. To do this, we decided to solve it graphically, so we created a line at 1.5 on our analytical solution, and we'll see where they intersect shortly.
Here you can see the plots that we came up with. Just generally, the Euler method was the least accurate, and then they increased in accuracy from the predictor corrected finally to the run cotta method, which was the most accurate. And they all show the same sort of form, so we're able to know that we plugged in our values correctly. In order to solve for that concentration at a time of 1.5 days, once again we created that blue line as seen on the lower right graph, and then we zoomed in and used our data cursor in order to find that the concentration will be 6.574 milligrams per liter at a time of 1.5 days. This just shows a summary of all the different methods. We then moved on to part B.
We were asked to solve for DO concentration in the same body of water over the same 6-day period using the Euler method, the predictor corrector method, and the analytical method.
The main difference with this is that we now have a DO to the power of m, and this m is a relaxation constant.
We started this the same way we started the last one, by opening a script file.
And then we defined both m values and k values in order to create less clutter in our plots. Once again, we defined our range and time interval for Euler and began to input our Euler for loop. The main difference between the Euler method used in part B as comparison to A was this differential equation for DO includes a differential equation for L inside of it. And we were able to input our value of negative KDL into this. However, we weren't able to solve for L, so in order to account for this, we used our previously solved function for L, which includes T, which we would be able to use. And you can see we defined two different functions for the different values of M. We then moved on to our predictor corrector method, which used the same initial concentrations. In the same way as seen in part A, we first created a predictor value and then averaged the slope at that predictor value with the previous slope in order to find a more accurate estimate of DO. And finally, we were asked to solve for DO analytically using our symbolic MATLAB, and in this case our m would be equal to 1 and not the previous values of 0.75 or 1.25. So in order to do this, we defined our symbols, and then once again we used MATLAB's existing function of dsolve. We had to hit the play button, which gave us our function, and then in order to plot this, we created a vector using a for loop for DO.
And same as in part A, we decided to create a 2x2 subplot matrix to display the different graphs.
All graphs show the same form, which lets us know that we are getting close to the correct values, and all have a minimal value for DO somewhere between 1 and 3. Clearly we know that our analytical method has the correct solution for DO, and we actually solve for that exactly as asked for in the problem by zooming in on our function, and we were able to once again use our data cursor to find that at the lowest DO concentration, which exists at a time of 2 days, the concentration will be 3.09 milligrams per liter. As we look at our m values, we can see that for the predictor corrector method, the m value does not have much of an effect. In fact, they gave exact same values for our oxygen concentration. We see the main effects of our m value in our Euler plot, in which our relaxed coefficient m of 1.25 makes the plot dip more and provides a lower minimum value of our dissolved oxygen concentration. Knowing this, we can assume that the best m value will be at 1. We'd like to thank you again for listening to our solution.